It will never be possible to run a rich machine learning model on just a few kilobytes. Or is it? That's what I thought until I met Danil and Blair from Newton, who came on the IoT show to tell me everything you need to know about the work they've been doing for the last 11 years at making it possible, allowing to bring machine learning models all the way down to tiny sensors. So we'll see today on the IoT show how that looks like. If you like this episode, don't forget to give us a like, hit that little bell there to get notified when we have new episodes, and leave some comments down here. Hey everyone, this is the IoT show. I'm Olivier, your host. Today we'll talk about AI on the tiny edge, all the way down there on sensors. And for that, we have Blair and Danil. Hey guys, how are you?
Hey Olivier.
Good. How are you doing?
I'm great. Fantastic. Survived the tornado bomb thingy that we had in the Pacific Northwest. Ran out of power for 3 days. I was missing it. Now I'm back with my lights and the camera and you guys. So that's perfect. How you guys been doing? So Blair, let's start with you. Tell me a little bit about yourself. Where are you calling from? Who are you? And how did you come up to being where you are in that company called Newton that we'll talk more about?
Yeah, well, right now I am currently in the San Francisco Bay Area. So I have the pleasure of getting all of your leftovers of the bomb cyclone that just occurred. So all of the rain that was in the Northwest, that's currently what I'm dealing with right now. Fortunately, I have lights at the moment, so I'm glad to hear that you were able to persevere. As for myself, I am the CTO here at Newton. I've had the pleasure of being with Newton for a little over 11 years, and I always like to say that I have all of the scars to show it because whenever it comes to growth, there's always some bumps and bruises in order to accomplish what you're looking to achieve. And as for myself, throughout my career, I had the opportunity to work with a number of different larger organizations. And when I joined Newton, one of the things that I was really compelled to join this organization about was really to do something different, really to set the industry in a completely different direction than what was expected. And as we continue in today's discussion, by the way, thank you for having us. We hope to not only give you some insight about that, but as well as the audience. So I'm pretty excited to be here to share our journey.
Me too. And I think this is the right audience here for this topic because you guys, yes, you wanted to disrupt, as you were saying, Blair, the industry and go in a different way, but not in a way that would be, you on your own. It's like a different way in terms of implementing something that others might have been trying to do and achieve. And many are still thinking today it's not possible. And we'll see what exactly that is. But I think it's an interesting thing. And 11 years into it, that means that you guys are doing something right. Because like a startup, 11 years old, would be dead if it was not something that not just investors but also engineers working in it were believing in, and so yeah. Well, I'm a strong believer. I think that you guys are doing more than one thing right, and we'll see what exactly. But Danil, what about you? So who are you? Where are you calling from? And tell us a bit about yourself.
Yeah, first of all, thank you, Olivier, for having us. It's a great pleasure. My name is Danil. I'm a data scientist. I'm calling in from Dubai. The weather is constant here, so nothing to say about that. I've been with the organization for 6 years, a little over 6 years, starting 2018, basically from the very inception of the Neuton.ai project. So my position in the company is head of machine learning. And I've been instrumental from the day zero, from the idea up until what it brought us today. So we have a working product, but I'm not going to jump ahead. We'll tell you all about it during our talk.
Definitely. And we'll get into some of the details. And actually, my first question for you guys, I've been trying to tease it a little bit, but what is Newton? What is this company about? So one of you, just go ahead and tell me what you think. What do you have to say about Newton?
Yeah, I'll jump right in. And I think you kind of hit on a couple of things that we really wanted to focus on. So even though I've been with the organization for 11 years, we really kind of began this Newton journey, as Danil mentioned, around 7 years ago. And we wanted to do two things. And when you look at it, you might kind of consider that they kind of maybe going in opposite directions. One is we wanted to be disruptive, but we also wanted to be inclusive. So, how can we do something that disrupted the market, but also ensure that we were including everyone as we kind of began this particular journey? And when you think about it, let's say as an example, when you consider Uber or when you consider Airbnb, both of those organizations began because there was a fundamental need that wasn't being addressed in the market. And in our case, one of the things that we really wanted to accomplish was how do we bring AI to everyone? And we really meant that in a very literal sense. And in order to also accomplish that, you had to also be able to bring intelligence to every part of the ecosystem, which included the edge at the particular time. So, number one, we wanted to make sure that we had a platform that enabled everyone to take advantage of all of these new technologies, these new approaches that we were bringing to the market, irrespective of their experience, whether they were a seasoned data scientist or whether they were just figuring things out along the way. So that was one of our core tenets that we wanted to accomplish. And then number two is we wanted to say, when you think about bringing AI to everyone, not only let's say, how can we bring AI, let's say, to what was being accomplished at the time, let's say your cell phone, let's say your wearable, but also we wanted to say, how can we bring intelligence to some of the older devices that was out there, let's say maybe an 8-bit MCU, or whether some of the newer devices that were out there along the way. And now more recently, we've had the pleasure of being able to produce models that also can be directly embedded into an actual sensor so that you have that intelligence literally directly on the edge. And that's something that certainly Danil will talk to the audience about moving forward as we continue today's discussion.
Great. So nice promise. I think I like the way you're approaching that, and you approach that to build up to where we're at today, bringing AI to everyone. I want to put it out there. We're not talking about generative AI. We're talking about AI, more broadly, which is artificial intelligence. I know there's a lot of buzz these days around generative AI, and but here right now we're not talking about that. We're talking about what I call boring AI, or productive AI, something that is actionable today. I have a bunch of questions, but first, Anecdote. On your website, there's a bust of Isaac Newton, and the name of the company, even if it's not written the same way, is Newton. So why is that? Why Newton? What's the relationship with AI? Was it just because it's a cool bust or something?
Well, it was a little bit of both, but I will say we didn't spend much time really thinking about our brand. It kind of really just hit us for a number of, let's say, obvious reasons. One, when you think about Sir Isaac Newton, he was a renowned mathematician, right? So it kind of really hit us right at our core. But he was also a key figure in scientific revolution as well as enlightenment. And what we're doing here in our organization at Newton is we've really flipped the paradigm completely on its head as it relates to our approach to being able to bring intelligence to the edge. So everything that we will discuss here today is something that we've developed completely 100% in-house. And we've completely destroyed the norm. So, and
In a
being
good
able
way.
to accomplish
In a good way. In a good way.
in a good way, in a good way, we decided, to tear everything down, build it back up, kind of like a phoenix, so that we really were now able to accomplish and help, let's say, the ecosystem, our peers, let's say, accomplish some of the things that we'll be discussing today. So,
Nice.
Newton is really close to our heart, as you might imagine.
I can imagine. So before we get into the how, I'm curious, why did you need to go and break everything and change the way things are done? What are the main reasons for you to really dig in that direction, go into that direction of breaking the mold, not doing things the way things were done, until now, or the way things are done by others, if I may say. So tell me about the why a little bit.
Yeah, it was honestly just practical experience. Just imagine you're in Europe and you can't get a cab, right? You're traveling, whether it's in Europe, whether it's in Asia, and you can't find any place to stay. And for us, it was the same thing. We were working with some of our customers who were looking to bring intelligence to devices that we, quite frankly, we struggled with using some of the tried and true methodologies and frameworks that were out there. And we just couldn't achieve some of our customers' goals. And we couldn't achieve some of the things that we were looking to accomplish, not only internally, but from a commercial perspective as well. And we really sat down and we say, hey, guys, if we want to move forward, we just literally have to do something different. And we've really demonstrated this in being able to not only create our own framework, which of course we've patented here in the US. We have a number of different patents demonstrating our accomplishments, but just quite frankly, it's really just simple. We were looking to accomplish something, and what was currently out there in the market didn't allow us to do it. So we wanted to not only develop something for ourselves, but for everyone as well.
I just want to add to that. I think a very important aspect here is technical. So the cornerstone of successful embedded AI is, I would say, three things: the accuracy, of course, the footprint, so that it would be able to fit on device, and inference time, so it would be able to have really quick inference, and the latency would be acceptable. So with traditional approaches like a neural network, which are 99% cases in the IoT world today, you can achieve acceptable accuracy, but not always you can achieve a certain footprint that will fit on your target hardware, or it will be on the limit. It will consume all your bandwidth, your application hardware, and it will also not execute very fast, because the larger the model, the more nodes in there, the more time to compute, and the slower the inference time. So what Blair has mentioned to flip the paradigm is a framework that creates a model that is capable to fit on any device, even the smallest ones out there, which were not even intended to be used for machine learning, or some older hardware that was never used for machine learning due to its constraints. So that's exactly what we did. And I just want to highlight one figure here. So the average size of the AI solutions that we generate with our technology is under 5 kilobytes of total footprint, flash footprint. And that is not only the model weights, as it usually is in many benchmarks, but also it is everything necessary to interpret your incoming raw sensor data, the signal, and to output prediction. That is data cleaning, filtering, feature extraction, pre-processing, then feeding into the model, and then the inference engine that needs to run to execute this model. All of that in under 5 kilobytes. And that can go into really any hardware, which made it possible, as Blair has mentioned, and I'll expand on that later, to embed these models directly into the sensors.
Yeah, because contrarily to any common belief, memory is not cheap, is not free. Compute is not either, especially as we multiply the nodes, the compute units, right? Not the nodes as in neural networks, but the nodes as in the physical compute units in a system, right? We're talking more and more about distributing intelligence. When you think about a car, it's not one compute unit. It's like hundreds, if not thousands. And so bringing the intelligence all the way down to every single compute unit, potentially. We'll see examples soon. You'll show us some examples where Newton can be used directly on sensors themselves. But here we're talking about running on very tiny objects, but many of them. So at the end of the day, we need to optimize in size, not just because of the sake of it, but also because the cost of it, right? You need to use less memory. because at the end of the day, that has a cost. You need to be more efficient as well in terms of processing with what you have in this kind of hardware. And interestingly, this is something that we've talked about smart devices for a long time. I remember when I started, working 25 years ago in the embedded space, we're talking about smart devices. It was about bringing software to the edge, not ML, not AI, but just software. Like if this, then that, right? So basically, and that was already about being smart, and there's a need for that. And so, I'm curious to know, what has changed? Some people might say, well, it's just embedded software, right? It's a piece of code. They have input, you have outputs, right? It's a function. And how much more complex would you say as things become for us to need a framework like Newton, versus, like if you think about a sensor like a motion sensor or temperature sensor, what are the functionalities you can achieve with more advanced software, and what did it take to go from normal software, I would say, to ML? Why do we need that, and what kind of scenarios can people think about?
Well, let's start from the very beginning. So a sensor generates some kind of signal, I don't know, temperature signal, for example, and without machine learning, you will be able to apply a set of rules. If it reaches a certain threshold, then, I don't know, bring some kind of signal or light up an LED and inform us about that. That's very simple logic. And if you want to try to extract additional pieces of information, for example, the temperature sensor is going to indicate how the temperature changes over time, and that temperature sensor, along with a CO2 sensor, might be in a container of bananas going across the Atlantic. A machine learning model trained on a sufficient set of data would be able to predict how much time does these bananas have until they get spoiled. So that would, in turn, inform somebody that they could go in and crank up the AC inside this container, for example, because they know that the transit is going to take longer. So that's a completely different type of intelligence. Traditionally, it is being solved with neural networks. Traditional neural networks, and it really doesn't matter. Is it TensorFlow, PyTorch, Caffe? It's the different wrappers around the same piece of mathematics. Those are beautiful technologies for many things, and they do excel at image processing, working with text, as we have seen the advances in the large language models. But they have certain limitations in terms of sensors. Now, as we have transitioned from rule-based models to machine learning models, we are currently in the state of using neural networks for that, traditional neural networks. And when we have started working on the Newton technical part, we quickly discovered a few flaws that traditional neural network approaches have into embedding the models into the edge. Namely, because you start defining the neural network architecture as an engineer before you even know whether this is going to be good or bad. So you're just maybe coming from experience or hypothesizing, okay, it's going to have like 3 layers, for example, 100 nodes in each, and this is how they're going to be connected. And only then they start training the neural network, sort of hoping for the best. And if it achieves a good enough result, then they think about, of course, they know before, they know how many weights, they can already calculate inference weight without even training it. But if they achieve a good result, then they proceed into compressing it, pruning it, quantizing it, and then embedding it on device. But nobody thinks that in a neural network, and our research shows that sometimes even half of the nodes may be redundant. They are there, they occupy a footprint, but their application within the neural network do not result in any change in the outcome. So it would be great if they were not there, and they would free up inference time and footprint, but you cannot get rid of them because it's a predefined architecture. So transitioning from machine learning traditional approaches, we have created our own neural network growth framework. So Newton doesn't have any architecture. We start with a single neuron, one neuron, connected to the inputs, and then train its weights. Then, with constant cross-validation, the framework understands, and all of this happens in fully automatic mode. The framework understands that there is more room to train, for example. It adds an additional neuron, and then it connects it sparsely, maybe to the previous neuron or other neurons, or maybe inputs. You might have a situation when you have one of the latter, maybe the last added neuron, which is connected to inputs, neuron number 2, neuron number 37, and so forth. So we call it selective neuron connectivity approach. Also, by the way, Newton doesn't have or doesn't use back propagation of an error or stochastic gradient descent, which is really impossible with any traditional neural networks. Instead, we have our own global optimization algorithm. We also have additional trainable parameters within each individual neuron's activation function, and all of them are individual as well, which makes these neurons so powerful. And having trained a neural network this way, node by node, growing its architecture as it trains, and the way it happens is every time it adds a new neuron, it freezes all the previous stuff it has trained and then only trains its weights. It makes sure that every single node has a purpose, has an impact on the outcome. And having trained a neural network like this, without quantization, without pruning, without compression, out of the box, is going to be 10 times, sometimes 100 times smaller and faster than anything you can achieve with TensorFlow. So this cornerstone with accuracy, and we did make sure that this approach does not compromise accuracy. We've tackled the other two aspects in a major way. So the footprint is reduced dramatically, 10 times, 100 times. And as a function of that, the inference time decreased dramatically, like 2 milliseconds, 0.2 milliseconds in many cases. So this is just some technical stuff on how this works.
Yeah, but thanks for describing it this way, because it does make sense, even for people who are not super familiar with how neural networks works. It does explain really well the differences, and that different approach that Blair was mentioning is like we're breaking the mold and doing things differently, because everyone these days is trying to optimize neural networks to have them fit down there with, optimization at the compile time or build time or training time, rather, and then optimization at transforming into machine code to have it execute down there. So yeah, definitely a different way of approaching the problem and addressing the different, I would say, limitations of classical neural networks. Can you give us some examples of applications, right, where classical neural networks might not excel or would be limited? Some example that you have using Newton in real life out there.
There is this company in the United States who are making smart tags for logistics. It's a label with a barcode and address in there, just like a traditional one, only slightly thicker, that contains a very small battery, a very small chip, and really resource constrained because it's disposable. The package is delivered and you throw it away together with a cardboard box. Mm-hmm. So the goal was to keep track of the fragile cargo, and if something happens, the model needs to recognize what has happened. And imagine the model that has to run on a few kilobytes of flash and has to last for a few weeks of delivery. It cannot be like a multi-layer neural network perceptron, CNN is going to just drain your battery really quickly. And the model that we built for these guys recognizes the following states: idle, when the package is in the warehouse. Then somebody picks it up and starts carrying it. That's another class, transported by courier, we called it. Then in a car is another class. Shaking, free fall, impact as it falls down, wrong orientation are all separate classes, and they are recognized in real time, spending just 2.7 kilobytes of flash footprint. And that was the most important. It's capable to last for over 2 weeks on this hardware and deliver the result to these guys.
So is it so basically it's a like motion sensor and Newton used to apply intelligence in that, and a little bit of power used. But like in practice, is that thing kind of waking up from time to time or on events? How do you make sure? Usually when we think about battery saving on embedded devices, we think about how long can it stay idle and not do anything, right? Versus how to be more efficient on when it's active.
I'll give you another example, an easy one to for everybody to comprehend. So every smartwatch has a fall detection model, like an Apple Watch, for example. And if they fall down, then everybody's notified and some business logic happens. So imagine how many times per year do you fall down? I didn't fall down for a few years at least, I believe.
Mm-hmm.
Nevertheless, the model inside my watch was active all the time, interpreting these non-fall, every fraction of a second. Now, the way it works currently is the sensor is running 24/7, streaming the data to the MCU, for example, at 100 hertz, 100 times per second, and that MCU is running this model apart from many other things in a smartwatch. Mm-hmm. And basically producing blank results, non-fall. So, but the sensor is running 24/7 anyway. So if you put the model in there, your host MCU is sleeping or doing whatever it's meant to do. Mm-hmm. Where the model inside a sensor at the tip of the sword, where the signal is generated, is not sending the raw sensor data, but is making predictions all the time. And only when the subject falls down, only then it sends a signal to the host MCU, which then executes business logic. In this particular example, it would be, I don't know, thousands of percent difference, I guess, if you can say it this way. Another example is not even working with sensor, but how a really small optimized model can benefit the consumer. We have this very interesting use case with the smart rings. So it's an Indian company. They manufacture them at scale. And imagine the constraints in a device like that. Okay, it's slightly bigger than this one, but you have a very small battery, a small chip, and you cannot be running a model with accelerometer and gyroscope with the 20,000 parameters convolutional neural network. It has to last for 5 days. And your model is the last thing they care about, is just the additional edge over the competition. Mm-hmm. And so we've been working with these guys to produce a really small model to recognize fitness activities, 7 different fitness activities. The subject goes to the gym, they activate the fitness mode on their phone, and then the app tracks how many times have they did different types of fitness activities. So you can, of course, achieve it with a traditional neural network, but it will work for 1 day, and then you have to recharge it. So these are some obvious benefits.
And I think that's one of the things that I kind of want to highlight to kind of summarize a couple of the different use cases that Danil just mentioned. When you think about logistics, or you think about global logistics, I mean, that's a solution and a business requirement that's been along for some time, right? Being able to track packages, whether it was on land or sea or et cetera. But when you think about, let's say, global logistics, historically, they've always tracked packages. Let's say they're tracking a shipment or a container that's coming from Europe to the United States. And historically, in tracking these packages, they would have to send the data, as an example, to the cloud, and then make determinations on if whether or not there's going to be spoilage, if whether or not they can expect for a particular shipment to be on time. And that takes compute. That takes, some form of labor on the back end side. Where if you're leveraging a solution, if you're leveraging a solution like Neuton, now that particular decision making is being able to occur real time, right? And you're able to make decisions much more efficiently. So that's a tried and true solution, or a tried and true requirement that's been around in the market. And then on the other hand, you have a smart ring that is now you're bringing intelligence, you're bringing new variables, to the market, right? That didn't exist before. And you have a solution like Neuton that's, let's say, allowing us to enable those customers to bring something completely new to the market. And that's one of the things that we're really proud of. We're able to optimize some existing solutions or enable new solutions moving forward.
Nice. So you have a little demo here on some hardware. I think Silicon Labs Cortex hardware, something like that. So how about you show us this little demo to show how things are working? Describe the hardware real quick, and then show us how things are working. I think showing is better than telling. We've been telling a lot right now about all of that. I want to see a little bit.
Yeah. So here I've got a Silicon Labs development board. It's got Cortex M33 chip. It's got, I think it's 32. No, I don't remember how many kilobytes. But nevertheless, in any case, the model uses, I think, 3.2 or 4.2 kilobytes. and accelerometer and gyroscope. It has many more sensors like Bluetooth and microphone, but we're not using them since it's a development board. We're just using the accelerometer and gyroscope. So the model we've trained is a buttonless remote control. And basically you just do different gestures with the device in your hand. Let's say it has a prettier packaging without buttons, and then something happens. You control your peripherals, or I don't know, PowerPoint presentation like a magic wand or HVAC. So you've got my screen, right? And I'm just going to connect to the device. So predictions are being done on device, and the classes are being streamed to the console. So it's got 6 classes. For example, double thumb tap. Okay, you see double thumb up there. So that could be programmed to do whatever you want. I don't know, turn off the lights, for example. Or double knock. I think double tap is what we called it. So I just, like I'm knocking on the door, right? If you want to switch tracks, for example, swipe left. Okay, swipe left, swipe right. Swipe right once again. So the more challenging ones were the rotations. Let's say I want to make it louder or warmer, for example. So I do the rotation, and it's recognizing that I'm doing rotation right. Or going the other way around, rotation left. It's a very simple model. Well, it looks simple, but it's got a few challenges to overcome. Just like that, we've. By the way, this model was done in almost fully automatic mode using our platform, and we'll say more about that later. But really, the only challenge was to collect the data, to collect the label data, and the rest was handled automatically.
Yep. And that's interesting. Yeah, there's 2 aspects of it that are really interesting. One is we need to debunk this notion that, we've seen that already, right? You see these Wii remotes that you move around and there's gesture in there. But people need to realize that the compute is not happening on these handled, parts, right? The compute, most of it is happening down there. Or this thing, when the compute happened down there, running out of battery pretty fast. So basically, you can't run them on a AAA battery for a long time. Well, what you just demoed and showed could be, running into a TV remote on a AAA battery that will last 6 months or even more, right? And the compute will happen, the inference will happen on the device itself versus on a main unit that is in connected to a wall plug, right?
So this particular device, and we are working very closely with Silicon Labs, it has a CR2032 battery in here, and there is a slot. And these guys were so much impressed by what we did, we made a model for them that they're showcasing on different exhibitions, like a year and a half ago. And with the single battery that they had, in a box with a chip, they have been showcasing this model over and over, without having to change the battery or recharge. So AAA is a nuclear power plant for this model. It's not going to even notice it. So it can run on a really small battery for a really long time.
Yeah, and if I may add, one of the things that I always like to say is when you think about it, your memory is your real estate, and your battery is your currency. And if you kind of think about it and apply it to something that's a little bit more essential, let's say, for example, when it comes to public utilities and your drinking water, they want to have the ability to place sensors, let's say, as an example, in a river to be able to measure the quality of water. And oftentimes, these sensors are placed in remote locations that are not always easily accessible. So the importance of being able to have a sensor that's able to consistently read the quality of water real time, now you begin to understand really the importance of making sure that you have a model that, is extremely efficient. Because if you have a solution that is, let's say out in a place that is not always accessible, being able to ensure that that data is collected, those triggers are sent when it's extremely important for our daily livelihood, then you begin to understand why connecting those dots of having an efficient model that can extend the life of your battery becomes essential. More than just, let's say, as an example, my son playing with his Wii or his Sony PlayStation from time to time.
Yeah, no, totally.
Wanted to say that in sensor AI, the topic of our today's talk, is something relatively new, and it just appeared 2024 this year. It was made possible due to two things. So first, these smart, intelligent, programmable sensors appeared. The first ones were introduced by ST Micro at the beginning of 2024. And they've got two chips. It's basically just a sensor with a very, very small chip in there. It's 8 megahertz of operating frequency and I think 32 kilobytes of, they don't even have flash. There is no volatile memory, so program RAM. And there is also two sensors from Bosch that appeared this year. And they were never intended for machine learning. It was a compute for housekeeping, for really simple business logic. And since our models are fitting into those requirements, we just gave it a shot. So we just trained the model and read the documentation because they have a proprietary architecture of those chips and embedded the first model into the ST microchip. So basically anyone can do it if they make a small enough and accurate enough model. And since we were the first ones basically to do it, then ST Micro got so excited, they made us official design partners at the beginning of the year. You can find us on their website. So we're delivering lots of different talks on this subject across the world.
I'm not surprised that many people are getting excited because of the scenarios that Blair just described and that you just demoed as well, Danil. But I'm curious to know, what is the developer experience? People out there were watching this video. Usually they are developers, they are architects, they are makers. So they're curious to know, what would be the developer experience? Do I need to understand machine learning and to what extent? Mm-hmm. What kind of tools can I use that I already know and master today to leverage Newton and put that into a sensor?
Well, let's first look at it from a higher level. So how is the Edge AI project executed? You have some idea, right? So something to be predicted by some embedded device. Then this idea needs to, you have to validate it first of all. And to validate it, you have to have some kind of data that represents the activities or events, whatever you are trying to classify, or maybe there is a regression model. So the first challenge is to collect and label data. Like in the case that I was showing, so the way it happened was the engineers were sitting there and collecting this data for hours, different people with different hands, different way they set up their device because it needs to generalize on a lot of different people. And then label this data. So they know that this file is going to be rotation right, and the other one is going to be rotation left. So this is easy example. There are much more complicated examples where you have to have video to see what you are doing, and then using the video analytics, you label the data if it's a lot of data. So that's challenge number one. So that's what takes up some part of embedded engineering, to make the device be capable to collect data and then set it up with your PC, and then some manual labor, high quality labor, because the quality of data directly represents the quality of the model you're going to build. So you have to do it with care. Challenge number two is then, so you got the data. You've got, for example, accelerometer and gyroscope, like from this model right here. So what are you going to do with it? You need to be, you need to have data science experience to be able to understand the data, to see what are the flaws and problems. Maybe the sensor was misplaced, or maybe there are some spikes that are not supposed to be there. Maybe it's really high frequency that you need to filter it. All these techniques need to be taken into account. Then you need to extract features from the data. So how a machine learning model like that from a traditional signal is going to recognize what's happening. For example, you are like in our case, so this is the activity, right? It takes maybe half a second to do it. Let's say 1 second. You need to represent 1 second of sensor data as informative features. What was the maximum value? What was the minimum? What was the mean crossing rate? Maybe you need some frequency domain features depending on your application. So that's feature engineering. And after that, after having transformed your signal into meaningful features, now you need to be a deep learning expert to build a model that is going to take these features and your labels and then map them together in an efficient way to then predict on new data. Okay, so that's half of the problem. All right, so you've collected the data, you've trained on 80%, validated on 20%. Now, let's say it works. Now you have to embed all of that into a device. And let's say you've been using Python, which is the usual suspect in these cases. Now you have to make it as efficient as possible using C or some lower level programming languages. And that not only includes transforming your model using like a TensorFlow Lite Micro framework, but also all your feature extraction code, all your filtering code. And that is really one of the major parts of our IP. The data preprocessing part is so much optimized that it doesn't hardly take up any space at inference. So that's another challenge. And then you have to compile it, put it on device, and test it in real time. Mm-hmm. So all these things have to somehow be overcome, and with different types of expertise. We've since our technology is not proprietary, and as I mentioned, our network trains itself automatically, people cannot download it from a GitHub repo. But we've had so much traction as we developed it, so we decided to make a new TinyML AutoML platform, which does all these things that I just explained, apart from data collection, because that happens before. And it will take your data, it will transform it, extract features, train a Newton neural network, and then compile and validate it, show you all the graphs and pictures, and then you select your target hardware, it will compile it. So you will, it's a very simple API, just 3 functions, and feed sensor data, receive predictions. So it shortens the cycle of your experimentation and potentially even making a production-grade model. I don't know if we have the time. I can show you like in 3 minutes the way it works.
Definitely. We can definitely do that. So I'm curious to see that.
Okay, so it's very simple. It's free. You can just sign up with a Google account and just give it a second. And that's the platform. It's very user-friendly. So it's this is the main workspace. All your models are in here. You can come back to any one of them, look at analytics, download the model. But let's say you have some data that you collected for this particular experiment, or you downloaded a data set somewhere. So add a new solution. Here you select whether it's classification, regression, or unsupervised anomaly detection. Let's say it's classification. You give it some name, and next. And right away, you'll see the 3 steps. So it's a 3-step process. You upload your data, you define training parameters in here, and then you download your model down here. So you can upload and drag and drop in here, or let's just collect or use one of the uploaded data set. So assistive touch, okay? This is the data set that I uploaded. I'll show it to you in a second. So this is the way it looks. It's basically 6 axes and a label, so class 0 in this case. And all the examples of different classes are down below. So you just upload this CSV in here, it's going to parse it, and it's going to ask you, what is the target column name? You can say, well, you have to say, what is your target column name? So it's this one right here. There are different additional options in here. Let's not waste a lot of time. You can also use a holdout validation data set. Otherwise, the platform will do cross-validation. So let's just select target. This is one action that I did here, and we're done with the first step. Now onto the training pipeline. A few ways of using it. Since this is a signal preprocessing use case, we enable signal processing, and we're going to say, okay, I know that I've collected the data that needs to be or should be interpreted by windows of 1 second, because my activities are usually taking less than 1 second. I know the frequency of data collection is 100 hertz, so I can say in number of rows, and I want to say 100 rows is going to be the window of signal features extraction. And from this window, out of each axis, you can see here accelerometer X, Y, Z, gyroscope X, Y, Z. These are the features to be extracted. So it's got like a perfect balance of accuracy and footprint enabled by default, but you can go in here and enable any of these features, and all of them will be created in a very highly optimized C code for you automatically, and all these features that you select will also be a part of your inference code, which is going to happen on device. You have some edits in here, you can change the axes you want to use it for. And that's it. You also have a feature selection option. If you don't know what you need, you can select them all and just enable feature selection, and it will create them and then eliminate the useless ones. And the input data is 16-bit integer. It's a multi-class classification model here. Let's go with accuracy to interpret the model results, and quantization-aware 16-bit integer. So what are going to be your weights? They're not going to be floats. You can initialize them as 8-bit integer and polish them in 8-bit integer. So nowhere at the model training stage and at inference is going to be floating point operations. And your target hardware. So out of the box, we support these ones and a lot from Microchip, but of course it can be compiled for any hardware. It's silicon agnostic. Let's say the Cortex M4, for example. That's it, all your settings. You start training and it fires up a virtual machine and does everything automatically. Now, not to waste time, let me just show you the way it's going to look like.
And this is hosted, right? So Danil, you were saying virtual machines, everything is happening in the back end. The interface for a developer here is that web page you just went through. Nothing else, right? No local tools to be installed, no local processing. Everything happens up in the cloud.
Yeah, exactly. In Google Cloud, right here. Yep. So this is an example of a trained model. So that one is just training. This one was trained in 1 hour and 16 minutes. Okay. And this is the accuracy we achieved, validation accuracy 94%. This is the footprint, and it's not estimated, it's compiled. And it's broken down into model, inference engine, and signal preprocessing code. This is the RAM footprint. And you've got all your metrics in here for multi-class classification model, feature importance matrix, confusion matrix. But this is really cool here. Let's say, and this maybe not the best example, but for some more complicating problems, you might have so this chart here says the flash increment with accuracy. And in some cases, it goes quickly into the maximum accuracy, let's say 95, 96, 99%, and then has a very, very minor increment and builds a lot of models and increase their size. Let's say this was that case, and let's say you don't want 94.3% accuracy, you want 94.1% accuracy. And this may be one of these models right here. And you just click that, everything recalculates, all the analytics as well, and you just download a C library. Everything compiled for the hardware that you selected. In this case, Cortex M4F. And then you can proceed embedding this into any edge device. There's a manual in there. And also there is a CLI tool to predict with Windows, Mac, and Linux. In case you don't trust this validation value, you can validate on your own holdout portion of the data just on your machine without having to embed it. So this makes it very, very easy to assess and then use.
Yeah, very, like, all in all, what you just demoed here is that I don't need to be a data scientist. I don't need to be an embedded developer. The embedded developer will do the job of integrating that library into their code, because that's no easy feat either. The collection of the data, maybe so the two far ends of the process of things that are very specialized. So it might not make sense to have a generic process to do that, but everything in between seems to be covered. It reminds me of there are other solutions out there. Edge and Pulse is a good example. They also have an experience which is cloud-based for the development and creation of your models, neural network based, and different examples. Actually, that's interesting, because my question to you guys before we point people to some resources is, when is it a good thing to pick Newton, and when is it not? If I were to approach things as in, hey, well, that's a Newton, case, or maybe Newton is not what I need here, and maybe you go directly to a TensorFlow, whatever, or you use Edge and Pulse and all the tooling from them. So at a very high level, what would be the rule of thumbs on your from your perspective there?
Yeah, I'll touch on that. I think you highlighted a couple of different areas. So one, when it comes to generative AI, as an example, Newton is not, that's not an area of focus. Also, let's say when it comes to video or images, that's an area at this time that we're not exclusively focused on. And we do also work on some use cases from an audio perspective, but at the time, that's not also an area where we're, really kind of honing in. But what I would say, and it really kind of, let's say, steps back to one of our tenets as it relates to being able to bring AI to everyone. So if you're new to AI, as you just mentioned a few minutes ago, we really encourage you to take advantage of our platform. Danil mentioned that it's free, so you have the ability to log on to our platform, take advantage of some preloaded use cases and models that are there so that you can really begin to take advantage of really leveraging this technology and maybe advancing from there. But also, let's say if you're a seasoned data scientist as well. I don't, let's say, necessarily want to date myself, but one of the things that I used to always hear is, how can I do more with less? Right. So if
Mhm.
you find yourself in a position where you have an existing solution and you need to have a more optimal model, you need to be able to have faster inference. You've ran out of space. You can't really change the architecture of your existing solution. We work with a number of different customers that where they say, "Hey, we can't change any of our hardware, but can you help us have a more optimal solution so that we can have more space?" As an example for our business logic, or you may be, let's say, on the research end of things and you want to be able to look at being able to do something different. One of the things that Danil highlighted that I thought was extremely important and it's also really revealing, is that when you look at, let's say, smart sensors and you look at programmable IMUs, when those solutions were developed, let's say by the likes of ST Micro or by the likes of Bosch, their intention was not to develop those particular sensors for artificial intelligence. That wasn't their intention at all. But when they had the opportunity, let's say, to work with us and understand what we were doing in this particular space, now they were able to leverage those particular breakthroughs and now say, hey, now we can bring intelligence directly to our sensors, et cetera. So you
Mhm.
may be, let's say, as an example, on the research side. And lastly, and one of the things that you asked us was, how did we get in this particular space, right?
Yes.
What kind of prompted us, right? And one of the examples that I mentioned to you was, if you look at Uber and you look at Airbnb, those organizations and those solutions were developed just really out of a basic need that wasn't being addressed. So if you find yourself in a situation where you're looking to address something that you haven't been able to accomplish before, and maybe it's bringing intelligence to, let's say, an older device, let's say like an 8-bit MCU as an example. Maybe you have a device that has not been supported by other platforms and other frameworks. Whereas with Newton, we are device agnostic. So you might find yourself in a situation where it's just something that you haven't been able to address. Then we highly encourage you to take advantage of our platform. And then, of course, we have, let's say, the likes of your organization and yourself who really kind of focus on bringing awareness uh, to the market on such technologies and the direction as to where the market is heading, then we certainly encourage you to take a moment and look at what we're doing in this space as well.
Yeah. And I know people will. I know people will go check out the link we're going to put down there, because the talk track what we discussed today, as well as the demos that Daniel just presented, are more than relevant for the audience here. I'm fairly sure they're going to try it out. So, guys, that was a very interesting, insightful deep dive. We wanted at the beginning to talk high level, but we couldn't resist, and we dove into it. And I like that a lot, and I'm sure the audience will like that as well. So we'll put that link down there. So recommendation, I guess, is go on the website, try it out. It's free. You can definitely engage there. Feedback for you guys as well. I guess it's this
Absolutely.
great if developers are able to come in and say, "Hey, I need that. I want this," and they can reach out to you guys directly as well. Well, thanks a lot for your time, both of you today. I hope the wind will not break anything on your side, Blair. And because you don't know anything else but sun on your side, Danil,
Yeah.
I'm just like,
Enjoy it. Enjoy it while you can.
Yeah.
exactly, exactly. Well,
Thank you,
thanks you
Olivier.
both. Have a great end of your day, and talk to you soon.
It was a
All right.
pleasure.
Thank you.